Let's take a look at an example. We have a system of equations ax equals b, where this is the coefficient matrix A, this is vector b. We want to express the general solution of the system as a sum of some particular solution to the system plus the general solution of the homogeneous system. Okay? So xp is a particular solution to the system. X sub h is the general solution to the associated homogeneous system. Okay. So how do we go about doing this? Well, we could start by solving the equation ax equals b. So we know to do this, we want to construct the augmented matrix. Let's be very clear here. We are dealing with the non-homogeneous system. So let me label it ax equals b. So we know we're dealing with the non-homogeneous system here. 5, -4, 2, 3, -3, 4, 4, 3. And then in the augmented part, vector b, -23, and 9. Okay, so I'm going to let the computer do the hard work. I'm going to make sure I input my matrix. I'll call it M. 5, -4, 2, 3, and then -23 in the augmented part, and then row 2, -3, 4, 4, 3, and then in the augmented part 9. And let's get the reduced row echelon form of that. And there we go. Quick and easy. The reduced row echelon form of the matrix is 1, 0, 3, 3, -7. And then row 2 is 0, 1, 13 fourths, 3, -3. Okay. So let's solve this system. So first off, notice I have two free variables, right? I have two non-zero rows, but I have 4 columns. So 4 minus 2 equals 2 free variables. Your columns without a leading term are your best choice for free variables. So I'm going to choose my last 2 variables to be my free variables. Okay. So I'm going to set x4 equal to t and x3 equal to s. Okay. Let's go x2 now. Let's use row 2 to find x2. So if I look at row 2, that's 0x1 plus 1x2 plus 13 fourths x3 plus 3x4 equals -3. And I'm just going to plug these in. So I could express my solution in terms of my free variables s and t. And so I'm just going to solve for x2. x2 is equal to -3 minus 13 fourths s minus 3t. And finally, let's use row 1 to find x1. So converting row 1 into an equation, I get x1 plus 3x3, but x3 is my free variable s, so 3s, plus 3t, but 3x4, but x4 is my free variable t, so 3t, equals -7. Solve for x1. I get x1 is equal to -7 minus 3s minus 3t. Okay, put all that together, I get the general solution to the system. Make this a little bigger so I can really spread out here. Okay, x1, the constant component is -7. Minus 3s. So that's minus 3s. Minus 3t. Minus 3t. Okay? x2 is -3 minus 13/4 s minus 3t. So that's -3 minus 13/4 s minus 3t. Okay? x3 is just s, so I don't have a constant term. I just have one s and no t's. And x4 is just t, so I don't have a constant term. I have no s's and one t. All right? Now, this is the general solution to, or I should say, one way to represent the general solution to this system of equations. We haven't quite finished what we need to do, though, right? We've solved the system, but we want to break our solution into a particular solution and a general solution to the homogeneous system x sub h. Now, you do this just a couple times, and you'll be able to quickly see that this constant vector here, that's a particular solution. Okay, and we could see that because if I set s and t both equal to 0, then I just get this last vector, and so it must solve the system. It is a particular solution. Okay, these guys with the variables, that is my general solution to the homogeneous system. All right, and we can check that if we solve for the homogeneous system. So I have one matrix M. Let's get another matrix. I'll call it H for homogeneous. Okay, it's going to be almost the same thing. Almost the same thing over here. But all zeros here. And remember, when we have all zeros in the augmented part, we customarily don't write them out because we know as we do elementary row operations, those will just stay zeros. Okay, I'm just going to get our coefficient matrix. Well, actually, I think I could just call it A, couldn't I, if it's just the coefficient matrix. So 5, -4, 2, 3, -3, 4, 4, 3. And let's get the reduced row echelon form of that matrix. Notice the reduced row echelon form, those first 4 columns are the same. So let's look at the homogeneous system just so we can confirm that this part over here actually is a solution to the homogeneous system. Okay? So we grabbed our coefficient matrix, 5, -4, 3, 3. Sorry, 2, 3. -3, 4, 4, 3. We have kind of imagined that the augmented part over here is 0, but we're not going to write it because we're lazy. And since we just know that's going to stay 0, we don't need to write it. Okay? The reduced row echelon form is 1, 0, 3, 3, 0, 1, 13/4, 3. Okay? And again, if you want to, you could just imagine, just know we have that augmented part with zeros over there. Okay? So if we solve this, the solution to the homogeneous system, again, we have 2 free variables. So x4 is t, x3 is s, x2. Find x2, let's turn this into an equation. So we have 0x1 plus 1x2 plus 13/4 x3, which is s, plus 3x4, which is t. And then in the augmented part that we didn't write down, it's equal to 0 because it's a homogeneous equation. It's a homogeneous system. Okay? Solve for x2. We get x2 is equal to negative 13/4 s minus 3t. And similarly for x1, we're going to use equation 1 here. We get 1x1 plus 0x2 plus 3x3, and x3 is s, plus 3x4, and x4 is t, and then it's equal to 0 because we're dealing with a homogeneous system. Solve for x1. We get x1 equals negative 3s minus 3t. And so if I look at the general solution to our homogeneous system, notice for x1, we do not have a constant part, right? So we just have negative 3s minus 3t. For x2 is equal to negative 13/4 s minus 3t. Again, no constant part. So minus 13/4 s minus 3t. x3 is just s, so 1s and no t's. And x4 is just t, so no s's and 1t. And this exactly matches what we have here. Okay, it really is the general solution to the homogeneous system. And so any solution to our non-homogeneous system, we can express in this form, where we have a particular solution to the non-homogeneous system plus the general solution to the homogeneous system. Okay? Now I want to say one more thing about this before we finish up. I want to point out that this solution, the way this looks, is not unique. Here I have chosen a particular solution to the system, but it's not the only solution to this system, right? Any particular solution to the system will work here. Okay? So for example, I could define my general solution as, so let's use a different particular solution. I could do -4, 0, 0, -1. This is also a particular solution to the system. I know because I can get there by choosing particular values for s and t. In particular, I chose s equals 0, I chose t equals to -1. Okay, so -7 minus -3 is -4. -3 minus -3 is 0. 0 minus 0 is 0. And 0 minus 1 is -1. Okay, so just a different solution to this system. Any particular solution will work. Okay. Similarly, there are different ways I could talk about my homogeneous solution. What I have here are two direction vectors, right? And I'm scaling them. And I'm saying that any scalar multiple of these direction vectors added to my particular solution here would still be a solution to the system. Well, if that's the case, then I can scale these vectors, for example, and still have a solution to the system of equations. So I could do, let's do 12, 13, -4, 0. So all I did is I took this first equation and I multiplied it by -4 because I noticed that it would get rid of the fraction and I'd get more positive terms than negative. This is pointing the same direction as this vector. And so I could scale, so anything I could scale this vector to by multiplying by s, I could scale this vector to the same vector, multiplying it by a different scalar. Okay? And same thing for this vector. If I scale this vector by any non-zero scalar, it would still work to describe my homogeneous system. Because my general homogeneous solution is any scalar multiple of this vector plus any scalar multiple of this vector. So if I take a scalar multiple of this vector, say 6, 6, 0, -2, just multiplying this by -2, if I scale this vector to anything by multiplying it by t, I can multiply this vector by a different scalar and get it to the same place. Okay, this is a different way to talk about the same homogeneous system. Right? So the point here is that there isn't one unique representation for this solution. Both of these describe the same set of solutions. Both of these solve the same system. Any point, any solution that can be described by this solution here can also be described by this solution here. We would just use different S's and T's. Okay?